So the same logical appliance, the same logical environment can be deployed on a number of resources, local clusters, local desktops, academic clouds like FutureGrid, Amazon EC2, a commercial cloud, and avoiding dependence on the configuration of the host. So making minimal assumptions about the VM available in the provisioning software, having nothing specific to a particular VM technology, and minimum assumptions about networking. Again, being able to do net traversal helps because now you can deploy virtual machines that are in a net environment in order to deploy virtual machines without requiring them to have public network addresses, which is a hassle. So at the end of the group VPN initialization, recall from the last lecture, the group VPN's website is used to set up users and groups. So each node, a user, for example, deploying a virtual machine will get this configuration, but once it plugs in this configuration as a virtual floppy that attaches to the virtual machine, the virtual machine can be turned on and it will go through the process of configuring itself automatically. When the user deploys these virtual machines on multiple cloud infrastructures, for example, they can log into the virtual machine, and after logging into the virtual machine, submit jobs and terminate the VMs when they're done with a batch of job executions, for example. The system has been deployed in real environments. Here's an example of a Planet Lab overlay with around 450 nodes running IPOP, bootstrapping infrastructure. And here on the right-hand side is an example of ramping up a cluster with hundreds of CPUs across multiple institutions: University of Florida, Northeastern University, University of Minnesota, Texas at Austin, Florida State University. And what you see here in the sudden jumps of resources, this is a HT Condor monitoring system that shows the number of available resources at any point in time. And these sudden jumps here are clusters that are turned on with these virtual machines running on nodes of each cluster at these different universities, and they connect together to the HT Condor pool and form a increasingly larger pool of resources from which users can draw when they run simulations in this particular system for computer architecture, research, and education. Here's an example of using user interaction with the grid appliance. I'm showing here a Unix terminal where I'm logged in to a grid appliance, and I have files here, and I'm connected to a pool of machines that are running the HT Condor middleware. So I can run a command, for example, that will show me the status of all the nodes that are connected to this virtual appliance pool. And you can see these are nodes that belong to my virtual network. This happens to be a publicly open virtual network that anybody can join to test out IPOP and to test out the grid appliance. So you see resources here with a memory, different sizes of memory. So these could be, for example, a desktop resource running 512 megabytes of memory, or a server on a private cloud, for example, running a virtual machine with 2 gigabytes of resources. But these are machines that are all connected together by a virtual network that allows Condor to run regardless and connect these resources regardless of where they are deployed. So my virtual machine has this particular name associated with my IP address. And I can, for example, try to reach another virtual machine by pinging it. So I'm going to choose this one, C212.240.072.IPOP. And what you see is, notice the first couple of packets took a long time, the round-trip latency of 2 seconds and 1 second. But after the third packet, you're actually able to create a shortcut connection. And you see that the latency dropped to around 84 milliseconds. And all this has been done automatically without user intervention in the configuration of these paths. Now, to show you an example of submitting a job in Condor, here's an executable that I'm going to submit for execution on a number of virtual machines. Let me show you the configuration of Condor here. I'm going to provide arguments and queue the execution of 5 jobs with these arguments of this executable. And this executable, this is a demonstration that shows it estimates the value of pi by running a Monte Carlo simulation. So it's a simple demonstration program. So I can submit this job by saying Condor submit and providing the Condor script. And now my 10 jobs are queued for execution, and some of them are already running. As you can see, the state is running, some are idle, and if I keep checking, at this point they actually all completed. The 10 jobs were submitted, they ran elsewhere, and they already finished. And I can take a look at the output of these jobs. So this is an estimate of pi, and if I look at another job, it estimates a different value. A different value for pi. So this is a typical high-throughput computing simulation where you run the same executable with different parameters or with random inputs, and you batch the execution of large number of tasks, and Condor, HT Condor is responsible for taking these jobs, running on a pool of resources and taking the results back. And what the grid appliance and IPOP enable here is the ability of Condor to work within these virtual machines that could be distributed all over the world.